Great, thank you so much. Thank you to the organizers for the invitation to talk about the SCC with you all today. Max did a great job setting this up. I'm basically going to give you a window into some of the inner workings of one of the models that led to updated SCC estimates recently. And I want to highlight throughout this talk how these updated models allow us not just to improve our estimates of the SCC, but also to begin to unpack the inherent inequities in the climate change problem. This is all collaborative work with the Climate Impact Lab. We're an interdisciplinary group of economists, climate scientists, computer scientists working to build high resolution projections of climate damages over the coming century. So I don't need to motivate this very much because Max did such a great job. I just want to put this in one given perspective. So the idea here is that all of the motivation factor behind the SCC is simply that mitigating greenhouse gas emissions is expensive. And so policymakers are trying to weigh the costs of that mitigation against these diffuse benefits that occur to many diverse populations around the world across many different years into the future. And so the SCC comes in by monetizing those benefits of avoiding a ton of emissions so that policymakers can weigh in an apples to apples way the benefits and the costs in the same sort of monetary units. Max gave you a great history of how the SCC has evolved, particularly in the United States, and it's been used and adapted in many countries around the world. I want to just put sort of a cherry on the top of that history and pointing out that very recently we have an indication that the SCC is going to be used in a much broader set of policymaking. So in September, the Biden-Harris administration announced orders to agencies to incorporate the SCC into many different government decisions like procurement, international aid, budgeting. And this has implications for the billions of dollars a year that the US government spends and things like its very large vehicle fleet of 600,000 vehicles. And so I think this is more motivation for us to get the number right and to think broadly about how this tool can be used to solve the climate problem in a much broader set of policies than has previously, at least in the United States, been used before. You don't need me to tell you why the SCC needs updating. Max did that really well, but I am going to focus particularly today on the damage function component of this. Many other components of the original SCC estimates needed updating, but in particular, I'm going to focus on how we build accurate climate damage estimates and these damage functions. One component I think that maybe we haven't talked enough about when thinking about why we should bother updating these SCC estimates is I think that spatial and sectoral resolution of newer SCC models are not just nice to have features, but I think are really important in building policy relevant metrics that come out of these processes. So on the one hand, when we're building aggregate SCC numbers of the total global damages that are designed to inform mitigation policies, we are going to get those aggregate climate damage numbers wrong if we mischaracterize or fail to characterize heterogeneity around the world. And that's just because all of these systems are highly nonlinear. So using aggregate damage functions and aggregate exposure to warming is really going to miss the overall number when we think about the extreme amount of heterogeneity that we see around the world. But the other reason is thinking about adaptation. So we've been talking a lot about the SCC and mitigation, but regardless of what we do on mitigation in the coming decades, we have a huge adaptation problem going forward. And local individuals, governments, businesses cannot appropriately plan for the future and thinking about resiliency if we don't have highly resolved estimates of climate impacts that are sector specific. And I think, I've been enjoying watching this debate between Max and Jim from afar about how much effort we should be putting into this type of damage calculation going forward. I think it's an important debate to be having. I think one thing to add to that debate is the importance of adaptation and the importance of better characterizing damages if we are trying to inform not just mitigation policy, but also adaptation policy. There's sort of no better example of the importance of these heterogeneities than last summer's devastating floods in Pakistan. You're seeing a picture of that on the left that were happening at the same time as we were getting a heat wave across the United States. The human welfare implications of these two events, both of which are driven by the global process of climate change, are obviously very, very different. So part of what we want to do is capture those differences as well as get the overall SCC number right. So Max laid this out really nicely. We are in an era for SCC estimation where we can do a lot more than we could in the past. This is mobilized by increasing availability of data, econometric methods, computing resources that are now at our disposal. And so we want to be and can be building SCC estimates that are built off of empirical, data-driven evidence, the best available climate science. We want to be globally representative, not just taking data from places that are wealthy, where data is easier to access. We want to think about adaptation into the future and value uncertainty and inequality. Unfortunately, the SCC space is full of annoying and difficult to remember acronyms, and I'm just going to add another one in for you. Our model that we've built to sort of answer this call is called the Data-Driven Spatial Climate Impact Model, or DSIM. The only thing I would ask you to remember about this is the data-driven and spatial part. So the idea here is we want to meet this call for updated SCC estimates using an empirics-forward data-driven approach, and one that is spatially resolved so that we can inform not just mitigation policy, but also thinking about adaptation. We're going to be building climate damage estimates at the scale of about 25,000 regions around the world, and thinking really hard about uncertainty in many dimensions, but particularly the climate dimension. So we're going to be using probabilistic climate model representations that think about the full uncertainty of warming that we face going forward, but also uncertainty in the spatial distribution of that warming. There was a really interesting question about tipping points earlier. I want to address that right now. I would say explicitly, we are not integrating tipping points. I think the question asker was correct that that's a really important thing to think about going forward. But this characterization of uncertainty does include some really extreme climate scenarios. So we have climate models, low probability, but they're in here in this distribution. Climate models are projecting warming up to 8C into the future. Given the nonlinearities in our damage functions, those are going to lead to some really severe damages. But I will point the audience and the question asker in particular to work by James Rising and Simon Dietz, and co-authors focus on explicitly trying to update these models to take into account tipping points. I think there's a lot of progress being made there. The other key feature of our model is that we're thinking about impacts that are empirically derived and heterogeneous around the world. So what you're seeing on the right are examples of what Max called a dose-response function, where you're seeing some outcome of interest, in this case, mortality risk on the y-axis and daily temperature on the x-axis. And the global average dose-response function in blue, you can see really misses what's happening on the ground in individual locations. So in contrast, in Oslo, Norway, a very wealthy and relatively cold place, we see a very different response than we do in Accra, a poor place that experiences an extreme amount of heat. And so the idea here is characterizing these locally will allow us to build better estimates of the SCC, but also think about local adaptation needs. Our approach to this problem, which looks different than I think there are other valuable ways of thinking about this problem. We're taking a bottom-up approach, which means we're going to be building estimates in a sectors-by-sector fashion, in just seeing scenario assumptions first that come from other modeling groups about future population, income, emissions, et cetera, including some of the new probabilistic scenarios that Max pointed out in his keynote. These are the sectors we are currently tackling. Those are then integrated together along with a simple climate model and then valuation assumptions that involve discounting, inequality, and uncertainty to build an SCC. What I'm going to sort of give a window into today is how each one of these sectors itself has sort of a pipeline, starting with historical data on an outcome in that sector of interest and how it has responded in the past to climate events through an econometric model, and then pulling that through climate change projections and what we call a partial social cost of carbon, which just involves the damages in that one sector. And once we build that for each sector, we will combine them ultimately together into an overall SCC. But this is a bottom-up approach where we're going sector by sector and characterizing heterogeneous damages across these different sectors. This is sort of the outline of how we tackle this problem. We are a data-driven approach here, so we're going to start with data collection, build econometric models that importantly try to capture dimensions of adaptation that we think may be important. We want to think not just about the benefits of adaptation, but also their costs. I will briefly touch on this in this short talk, but happy to answer questions if people are interested. And then finally, we want to build those econometrics into climate change projections of the future, translate those into damage functions that allow us to compute an SCC. And then I'll talk briefly at the end about the many interesting welfare questions about how you take empirical damages and turn them into an SCC, thinking about inequality and uncertainty and discounting in a variety of different dimensions. Okay, so starting with data, our attempt here is to build the most comprehensive data sets we can for each of the outcomes of interest. I think this is a rapidly evolving space, and all of these maps could probably look better than when each of these projects started. But you'll see that there's a lot of heterogeneity in what is feasible for each of these categories. So here we're thinking in energy about energy demand going forward under climate change, particular changing heating and cooling demand. The data that we have are very spatially comprehensive, but also very spatially coarse. We're using country-level data at the annual scale from the International Energy Agency, including residential, commercial, and industrial electricity and other fuels. Mortality looks very different. We have much higher resolution data here, but much poorer spatial coverage. So we have subnational age-specific mortality records for a little over half of the global population, with really important omissions in key regions of Africa and Southeast Asia in particular. And I'll talk about how we try to tackle that going forward. In agriculture, we have subnational crop production data for 6 different staple crops, including crops that are very important as subsistence crops in key regions of the world. You can see the spatial coverage is maybe a little bit better, but we're still missing really important regions, and I think that's an important thing to think about going forward. In labor, some SCC models think about labor productivity. We're going to think about sort of the disutility that laborers are experiencing when they are faced with extreme heat on the job, and we're going to do that using time use data that tell, where an individual writes down what they do every 15 minutes for, say, a week, and you can get very precise characterization of how many minutes per day a worker is working. These represent about 30% of the global population, and again, there are important data gaps we're going to have to work to fill. And then our final sector is the coastal sector. We've constructed a lot of the data necessary to do this exercise. So downscale measures of both the exposure, so what type of sea level rise are we looking at, but also the hazard. So what is on the ground, what types of people and infrastructure and value of assets is sitting on the ground at high resolution that could be exposed to this coming hazard. And these data sets are all publicly available. So with that data, the next step in our approach is sort of the heart of a lot of our damage function calculations, which is to try to econometrically estimate how these outcomes have responded to climatological events in the past. We build on a very rich literature in climate impacts econometrics to estimate these models. These are now very standard at this point. We're just applying them to our particular setting. So for example, the way these models might work is to relate age-specific, location-specific mortality rates to flexible functional forms of temperature and precipitation in that place, using a suite of fixed effects and other non-parametric controls to isolate plausibly random variation in the weather. The idea is comparing mortality in Santiago under a year with a slightly hotter summer than to a year with a slightly cooler summer. We recover very standard nonlinear relationships in many of these sectors. For example, mortality has been studied extensively by economists and epidemiologists, and this sort of U-shaped relationship for the over 65 population is very common. Extreme heat and extreme cold both elevate mortality risk. So this gives us sort of an average sense of vulnerability, but what I've been talking about a lot is the importance of characterizing inequality and also characterizing adaptation, and that type of average dose response function ignores the fact that different populations are very differentially vulnerable. So we build on this model to allow the shape of that curve to itself depend on conditions in a given location. So for example, I'm sitting here in Santa Barbara. We don't get enough hot days for me to invest in air conditioning. I'm not very well adapted to a hot day, but someone living in the southwestern United States that sees those hot days all the time likely do have an air conditioner, and they likely respond in a given to a given outcome, whether that's mortality or energy, in a very different way than I do. So we're just going to build slightly on this model by including a vector of covariates that will shape that response function differentially based on the conditions in a given place. That can be income, it can be climate. For agriculture, that's going to be irrigation, etc. And visually, what this allows us to do is to capture differential vulnerability as we have seen it manifest in the historic record. So if we go, for example, to the coldest regions of the world, the figure on the right is showing you the marginal effect of a 35-degree day relative to a moderate 20 day for these vulnerable populations of 65 and over. And you see the death rate is projected to be incredibly extreme for this population in the places where those hot days are very, very rare and not expected. But reflecting adaptation we can see in the data, we see that in warmer locations, that marginal effect declines somewhat pretty substantially, such that by the time you get to the hottest regions of the world, this curve is much flatter. We're seeing very low marginal responses to heat in the places where these days happen a lot and people expect them to occur. This is important when thinking about average climate driving adaptation, but of course, income facilitates investments in adaptive technologies. And we see this really shining through in our work on electricity, where we see that the sensitivity is very much driven by income. So if you look on the right, you're seeing it now a dose response function for electricity consumption. We see people increasing their consumption both to respond to cold and to respond to heat. I actually lived in Chile at one point, and the lack of response was very notable to me. I was like trying to study in the middle of winter, and there was not a lot of indoor heating, and so we weren't seeing a lot of this increasing expenditure on electricity in order to respond to cold, which is what we actually see in the data. So while in the wealthiest regions of the world, we see this protection against cold and heat by increased electricity consumption, we don't see much of a response, even in slightly poorer locations. And for the vast majority of the global population, there's virtually no response. So these are not places where people are using energy services to respond to daily fluctuations in temperature. And that's really important heterogeneity to capture relative to what we're seeing in the wealthy regions of the world. That's going to be important when thinking about heterogeneity and vulnerability today, but particularly when we think about the future. Moving these dots forward under projected income growth means that we're going to have to think about a changing dose response function as people get wealthier and wealthier over time. Each of these sectors, we uncover sort of different drivers of vulnerability and therefore different drivers of heterogeneity in these response functions. So for electricity, we see that income is really important in facilitating investment in energy services to respond to climate events. In labor, it seems that the sector of employment is incredibly important in determining sensitivity. This aligns with prior work from the United States and a few other regions. So what this means is that workers who are working in what we call high-risk sectors, agriculture, mining, construction, manufacturing, we see a large drop-off in their time spent working when temperatures get very extreme. In contrast, for those of us that work inside in climate-controlled environments, there's no statistically significant relationship between daily variations in temperature and the amount of time that you work. And so when we think about this sector, both across the world and going forward, what's really going to matter is how many people in your economy are employed in these high-risk sectors today and going forward. And then finally, in agriculture, there's, I would say, sort of the econometrics of climate impacts really began in agriculture. There's an enormous body of work thinking about the weather conditions that matter for agriculture, as well as the covariates that may shape your sensitivity to those weather exposures. And so we take a little bit of a different approach in this sector, where we take some sort of basic machine learning tools to try to unpack which weather exposure measures and which covariates are best predicting the overall variations in yield. And this process leads to some pretty intuitive outcomes. So for example, if you look at the lower right, you're seeing how maize yields on the y-axis respond to variations in precipitation. And as you might expect, irrigation is really important here. So places that are very highly irrigated don't see much response to variations in precipitation. They're insulated from the impacts of drought and extreme, to some extent, extreme positive rainfall. But in places with no irrigation in blue, there's a lot of sensitivity of maize yields to dry conditions. We use this type of surface with a variety of different covariates and weather exposure metrics to build high resolution estimates of sensitivity for each of these crops. And you can see, for example, sensitivity of corn in Illinois looks very different. And in fact, something that's documented in Marshall and many other people's work in the past, we actually see in the United States much more sensitivity to heat than we do in places in South America, for example, in Mato Grosso and Brazil. So these econometric estimates allow us not just to characterize the shape of the response function, but also how it differs across populations, reflecting differential adaptation we can see in the historic data and can inform what we might see adaptation-wise going forward into the future. But the challenge with just taking that sort of what we call a response surface, so dose response functions that vary over space and time, and taking those forward into the future to calculate climate damages, is that those changes in sensitivity reflect the benefits of adaptive actions, but not their costs. So if you think about a heuristic mortality response function, for example, here at the top gray line, that top gray line reflects a very vulnerable population where death risk rises substantially under extreme heat and extreme cold. And we want to think about adaptation either through income or climatological adaptation, pulling that curve down towards a flat line. The perfectly adapted location or population would be one in which death risk does not vary at all with variations in daily temperature. But to achieve that flatter line, we have to pay some costs going forward. We have to invest in air conditioning. We have to change the hours that we spend outside. There's a variety of monetary and utility costs that we must incur in order to achieve that adapted state. And we want to generate projections going forward that don't just characterize those benefits, but also attempt to characterize the costs. This is a really hard problem. There's a lot of different ways to try to tackle it. We take one approach. I think there's a lot of other work that can be done to improve upon this approach. I don't have time to get into the weeds of it, but essentially what we do is build a revealed preference approach to try to infer what those costs of adaptation must be under a variety of stylized assumptions. So the idea here is that the full value of the climate impacts that we want to measure are not just the impacts from temperature hitting your outcome of interest, but also whatever adaptation you incurred to change your sensitivity from some original sensitivity we can characterize heuristically with beta 1 to a future sensitivity beta 2. For example, if we want our agriculture to look like it does in Holland with these highly insulated greenhouses that very closely control the climate, we're going to have to pay for the energy and infrastructure to achieve that, that resiliency. This, our approach here builds on a lot of prior work thinking about revealed preference and adaptation decisions. And the idea intuitively is that we are going to start by assuming that what we observe in the data are investments that people are making to optimally trade off the benefits and the costs of investing in adaptation. If we make that assumption that basically on the margin, people are equating marginal costs and marginal benefits of adaptation, we can use the fact that those econometric models I just showed you gave us estimates of the protective benefits. We can see how two different populations in slightly different climates invested differentially in protecting themselves, say, in terms of their mortality risk when we observe a hot day. We then use those estimates of protective benefits to infer what the cost must be under the assumption that people are making rational decisions and weighing marginal benefits against marginal costs. We integrate marginal costs out over the coming century to get estimates of total costs, essentially building revealed preference estimates of adaptation. I think there's a lot of exciting questions and work to be done here. This is making a lot of assumptions about rationality of investments in adaptation. I think there's exciting work about belief formation and expectation updating that should play into updates and improvements in thinking about adaptation costs going forward. So at this point, with an empirical estimate of dose response functions reflecting adaptation benefits, a revealed preference approach to try to capture adaptation costs, we can generate projections into the future of what climate change may do for each of these sectors at high resolution. The problem of doing this is one not just about projecting over time, but also about filling in over space. So as I made clear earlier, we don't have comprehensive data on these outcomes of interest everywhere. And so we face a spatial extrapolation problem like the one that you're seeing on the slide. These are the places where we have data. You're seeing each region colored by the marginal effect of a hot day on the mortality risk in that 65 plus population. We can see a lot of variation in our sample, but there's a lot of places that are missing. What we do is use that estimated response function that we've built from these observational data to infer what sensitivity must look like in the places where we don't have data. So for example, we have some really nice mortality data from Chile, but we do not from Argentina. So the idea is sort of a covariate matching idea in which we say which regions of Argentina look very similar in climatological in terms of their climatology and in terms of their income to certain regions of Chile, and can we infer sensitivity to heat for that region of Argentina looking at the variation we have in our observational sample. We do that to fill in this map so that it looks not just like this, but instead like this, to reflect heterogeneous sensitivity around the world. Of course, this is a massive amount of spatial extrapolation, and we expend like many appendix sections in each of our papers trying to probe the reliability of this assumption. But critically, this allows us to at least attempt to characterize heterogeneous sensitivity instead of imposing the assumption that, say, sensitivity we see of mortality to temperature in the United States applies to regions in sub-Saharan Africa. And you can see this sensitivity on the map reflecting, in this case for mortality, both the role of income and the role of climatology. So in cold regions, we're seeing very high sensitivity, but we're also seeing high sensitivity in regions that are very hot, but are sufficiently poor that investment in adaptive protective technologies and behaviors is infeasible. This is what our map looks like when we think about sensitivity today. But as we project into the future, now that we've sort of filled in estimates for the globe, we are likely to see hotter locations and wealthier locations into the future. And so you can see this map as we go forward begin to lighten, reflecting our projections of adaptation in the future based on the variations in adaptation we can see in the historic data. By the time we get to the end of century, you see a much more muted map indicating a much more adapted world than you would have recovered today. We can collapse these estimates to build sort of a time series of what we think these damages will look like going forward, aggregating across regions to get global numbers. We start with sort of a benchmark estimate that ignores adaptation going forward, so it doesn't allow people to invest in air conditioning or other behaviors and adjustments going forward. For mortality, we see that making that assumption of no adaptation leads to really extreme mortality rates around the world. Auto fatality rates in the US are somewhere around 12 deaths per 100,000. We're projecting over 200 deaths per 100,000 by end of century under that assumption of no adaptation. But we see really large projected benefits from accounting for the role of income in facilitating resilience and adaptation. So this falls to closer to 100 deaths per 100,000, falls even further when we account for the fact that gradually warming climate will induce people to adapt to their slowly changing conditions. When we account for those adaptation costs that we infer using revealed preference, this rises to somewhere around 80 deaths per 100,000 by end of century. These are highly uncertain projections. Max talked a lot about one of the exciting components of the NAS report that led to updates in the EPA's approach to the SEC is to take this uncertainty very seriously in valuation. We try to characterize uncertainty both in terms of the climatology, but also the econometric estimation that inherently has a lot of uncertainty as well. So both the damages and the climate are uncertain. You can see there's a really wide spread of damages here, even by end of century. For mortality, we're seeing even under a high emissions scenario that this includes zero. We build these types of time series for each different sector. So we see, increases in electricity spending to protect against heat, declines in other fuels in response to warmer winters that require less heating, increasing damages from sea level rise, declining labor supply, and for most crops, pretty severe changes in yield, although rice is an interesting outlier in that case. Those aggregate time series, of course, mask a lot of important inequality and heterogeneity around the world. What you're seeing here is a map of these damages at our impact region scale, where it's very clear that the lion's share of these damages are felt by the global poor. This is true not just in mortality, but largely in many other sectors, although there are some interesting outliers. One way to look at this is to plot damages against income deciles today. On the left, you're seeing that the death risk from climate change is largely borne by the poorest populations today, whereas we are projecting the relatively wealthy regions of the world to spend money on adaptation. This looks somewhat different in agriculture. So I think what's interesting to probe here with these types of results is how inequality looks very different in different sectors and in very different sectors of the economy. So for example, in agriculture, we're projecting very large losses in the bread baskets of the world that tend to be relatively wealthy and relatively temperate, although there are some concerning losses in the very poorest decile of the globe. Labor looks very similar to mortality, and that the poorest regions of the world are facing the largest impacts, and particularly the poor and very hot regions of the world we project to see the largest impacts. When we pull all these damages together and plot aggregate damages against global warming level, kind of doesn't matter what global warming level you want to project into the future. We're seeing the vast majority of these damages being borne by the lowest and lower middle income countries around the world. In some scenarios, if we achieve Max's goal of hitting 2C, on average, we're projecting benefits for upper middle and high income regions, whereas there's still substantial damages in the poorer regions of the world. This is particularly true if you're in a poor and hot place. So here you're seeing damages in a heat map against GDP on the y-axis and average temperature on the x. And really where the lion's share of these damages are manifesting is in the poorest regions of the world that are also hot. All right, so I said that we were going to talk about the social cost of carbon. Mostly what we've talked about so far are damage estimations and local level damage estimations. I want to spend the next few minutes wrapping this together into an SCC. So the way that we do this is you can think about each one of those maps being replicated thousands of times to reflect uncertainty in the econometric estimation and uncertainty in the climate. And then I'm going to collapse, after monetizing those damages, into one dot for each one of those projections, and then index that dot against global mean surface temperature. So each one of these dots represents a probabilistic estimate of damages, in this case for mortality, against the amount of warming from a given climate model. Under RCP 4.5, we don't see a lot of warming. Under RCP 8.5, we see a lot of warming, and this distribution allows us to construct an empirically derived damage function fit through these points. It turns out that we see in most of our sectors, we see evidence of a quadratic damage function, which is what Bill Nordhaus wrote down, many years ago, and we're really able to recover that in the data here. With these empirically derived damage functions, they look very different across different sectors. So we're seeing, for example, increases in electricity spending, but really substantial declines in other fuels, caloric damage function here in agriculture, reflecting lost calories due to yield losses going forward. These damage functions then allow us to pulse the global climate with just 1 ton of CO2, that's the SCC experiment, trace that change in CO2 through a change in GMST, and then through this damage function. So we take a simple climate model, we use the fair climate model that Max highlighted that came out of a recommendation from the NASS report. We pulse that with a ton of CO2. That leads to a long trajectory in changing CO2 concentrations and a long trajectory in temperature change. With those damage functions I showed you on the prior slide, you can convert that temperature change into a present value, or if you don't want to discount it yet, just a total value of damages for each sector. In this case, we're seeing mortality damages. The uncertainty here again comes from econometric uncertainty, but also over the FAIR model itself. So Max pointed out how these numbers have changed since over the evolution of updated SCCs. I want to focus on how these have changed in a sector-specific fashion. So our approach here has been local estimates that are also sector-specific. And what you're seeing on the right in the gray are original SCC estimates by sector for the fund model, which allows us to break out estimates by sector, and in blue are estimates for each of these sectors. And so not only are we getting very different overall numbers, which Max highlighted, but what's important for thinking about adaptation and sector-specific planning is that the nature of these damages also look very different. So we see much larger estimates for mortality, flipped signs for both energy and agriculture, and then we're adding components like labor disutility that weren't included before. All right, so pulling these sector-specific estimates together into an aggregate SCC, this is where a lot of the really interesting welfare economics comes in. There's a really rich, mostly theoretical literature thinking about how we conduct valuation when we are aggregating uncertain damages across heterogeneous populations and time periods going forward. There's a lot of work showing us that it can be critically important to think about how you value uncertainty, how we equity weight, as Max pointed out, how we deal with discounting, and we think we're in a unique position to sort of explore the quantitative implications of these theoretical insights because we have characterized uncertainty in a really rich way, because we have heterogeneity at the scale that we do, and that we can integrate probabilistic scenarios to think about endogenous discounting. In particular, when we're thinking about equity, the importance of equity weighting is going to depend on the resolution at which you can resolve climate damages. And so I think exploring heterogeneity and equity weighting becomes really interesting when we have something at the scale of, say, 25,000 regions instead of a few regions around the world. Here's sort of one window into what some of these estimates look like. We have taken a stance of you can sort of choose your own adventure here. I think that's important because policymakers around the world are approaching these valuation assumptions very differently. Max pointed out that equity weights are being used in Germany. They are not in the United States. And so we've been trying to produce tools to allow policymakers to explore different valuation assumptions. The only thing I want to highlight here is that these assumptions really matter, even with the same underlying toolkit in terms of thinking about how you value uncertainty, how you discount, and how you handle equity weighting. So for example, comparing the mean over uncertainty here to the equity weighting column, you can see that taking into account the fact that declining marginal utility of consumption means that $1 is worth a lot more to someone poor than to someone rich really matters for the SCC, not just because of heterogeneous incomes, but also because we are seeing heterogeneous damages. So people are valuing that dollar differently, but they're also experiencing very different dollar impacts around the world. we've been building this tool to integrate the probabilistic scenarios that Max highlighted coming out of RFF and Jim's work. And then the same infrastructure can be used to compute the social cost of methane and nitrous oxide. I think I have about 1 minute, and so I'm just very briefly going to talk about where I think we should go going forward. I think this sort of hopefully contributes to the conversation Max and Jim have been having about where to go from here. So I think one striking thing that's coming out of both our work, but also this graph on the lower left is coming out of the work led by RFF, is that non-market damages are critically important in current estimates of the SCC. There's lots of sectors that we haven't tackled yet, so I'm not saying that we don't know that this will necessarily hold true, but so far we're seeing that these non-market damages are really, really important, and that means that how you monetize them becomes critically important for the SCC. And so I think we need to probe a lot more how we do this, whether we should be doing this better, and thinking really hard about this monetization problem, because if we're building sector-specific damages in the way that we are now, these non-market damages really take center stage. How you monetize things like mental health or crime and conflict, I think, could be very important in the overall number and needs a lot more attention going forward. Max highlighted completeness, ecosystem services really jumps out here, but there are many other categories. But not just categories that are being missed, but I think dimensions of inequality that are very insufficiently characterized. We have a very crude way of thinking about heterogeneity, I would say, so far, and there's a lot more that can be done to better characterize differential vulnerability. Echoing Max, I think that thinking about GE here is increasingly important. There's a lot of exciting work being done on this. I think the interplay between non-market damages and GE is an interesting one. If these damages are really dominated by non-market factors, how do we think about GE components in non-market damages is really interesting. And then any time you look at the maps that I've shown you, it should jump out of the page that migration is likely to be very important. And I think we've got a long way to go in building empirically derived, but theoretically sound projections of what migration might look like and how that may shift adaptation and mitigation pressures going forward. So I'll just briefly wrap up by saying, hopefully Max and I have both convinced you that the SCC is important for thinking about mitigation policy, but also what we've built with DSEM helps us think about adaptation policy as well. We think that showing how inequality and uncertainty matter here for the SCC become really important for policy conversations going forward as the SCC gets used more and more in a broader set of decision making. Thanks so much.